Hello and welcome. Let's continue to look at the fault analysis using the Z bus. Last time we concluded on just introducing to you the symmetrical components and why they are important to find the unsymmetrical faults. So far, what we concluded was that we have these are the three types of unbalanced faults that you have. You have the single line to ground fault, you have the line to line fault, and then you have the double line to ground fault. Now, when we start using the Z bus to analyze these types of faults, then we have to understand the following. First of all, using the Z bus is a generalized format. When you are solving the fault analysis without the Z bus, it is assumed that you're looking at a very small system, meaning you've got very few buses. Now, in a case where you've got several buses in the system, then we need to use what we call the Y bus, which the Z bus, which now incorporates the understanding of the many buses in the system. In the general procedure, we have to assume that we know the pre-fault values, usually taken as 1. Usually, the pre-fault values are taken as 1 at angle 0 degrees per unit. And then we have the procedure as follows. We calculate the Z bus for each sequence, meaning you've got the 0, you've got the positive sequence, you've got the negative sequence, and you've got the 0 sequence. So you have to calculate the Z bus for each sequence. This is especially when we're dealing with unbalanced faults. Then for a fault at bus I, you have to calculate the Thevenin equivalent impedances. The pre-fault voltage is the positive sequence Thevenin voltage. So you remember in the Thevenin analysis, we were ending up with a V Thevenin with an impedance that is in series to a circuit. So that is the Thevenin's analysis system. And then to the terminals here, you can have now the fault impedance connected there. Okay, so this is the goal that we have to use to determine these parameters. Just a review, you remember these are the faults that we have, the balanced three-phase fault, the unbalanced faults, which are single line to ground, double line to ground, and then line to line faults. Why do we calculate these faults, and what's the reason to determine these faults? The most important reason is that we want to determine the ratings of the circuit breakers as well as the fuses. It also helps us to determine the impedance of the transformers and generators, as well as also helps us to develop the protective relay settings for the system. So it is very important for us to determine these faults and analyze the faults, because then we're able to set the fuses, select the right fuses, we're able to set the relays, protective relays properly, and we are also able to select the right ratings of the circuit breaker in the system. What we need for our calculations, for the magnitude of fault currents, these depend on the impedance of the network. Obviously, this is where the Z bus comes in. The internal impedances of the generators, the resistance of the fault, that is the arc resistance. Then we're also looking at the network impedances being governed by the transmission line impedances, transformer connections and impedances, grounding connections and resistances, And then the general behavior is divided into 3 periods. You've got the sub-transient period, you've got the transient period itself. So the sub-transient period is for a few cycles, doesn't last long, but then for the transient period, you have a relatively longer time, and then you have the steady state as the third period under consideration. So in the sub-transient period, where the generator reactance or synchronous reactance is taken as XD, and then we use this to determine the interrupting capacity of the high voltage circuit breakers, also to determine the operation timing of the protective relay system for high voltage networks. The transient period, the synchronous generator is taken as XD single prime. This is double prime. So we use this to determine the interrupting capacity of the medium voltage circuit breakers, and we use the transient periods to also determine the operating timing of the protective relay system for medium voltage networks. Equally, we utilize this transient period for transient stability studies. For the steady state, we are taking the synchronous generator reactance to be XD, and this is used for steady state operation. Well, for the method that we use, as already mentioned, the faulted network is solved conveniently by Thevenin's method. If you've forgotten the Thevenin's method, browse through in my videos. There is the Thevenin's and Norton's theorem covered, and this is usually covered in the first, second year modules. So here we have got the network resistances being neglected, and then the generators are modeled as an EMF behind the sub-transient or transient reactance. So similar to what I mentioned, where you have the generator modeled under this sub-transient reactance. Okay, so you've got your generator voltage there, or in short, this is what we call the Thevenin's, and this can be the Thevenin's impedance. Furthermore, shunt capacitances are neglected. The system is considered as having no load. If the fault impedance is 0, then it means the fault is referred to as a botted fault. Okay, so if there's a line, and if this is ground and there's a line to ground fault, for instance, if there's a fault that goes without considering the impedance, the fault impedance, then this is called a botted fault. Whereas if we have a line, let's say this is 3-phase, phase A, B, C, or line red, yellow, blue. So if you have lines and then you have a line that is connected to ground via a fault, so this fault now has got the impedance, the fault impedance, what we consider the fault impedance in between is created. Then this is a different case scenario. Let's consider a balanced 3-phase fault using the Z bus. So in this case, we have a 3-phase network. So we're just taking a single line diagram here, ignoring the other 2 phases, although the system is considered a 3-phase system. And the transmission lines are represented by the pi model, and all impedances are expressed in per unit on a common MVA base. The fault here is applied to bus K. So this is bus K, where the fault is applied. Usually the faults are on the transmission lines, but we shall look at the cases where those scenarios are considered. So when we have a fault at bus K and we have a fault impedance, so it's developed through a fault impedance ZF to ground, then the pre-fault voltages that we are going to have, which can be calculated from the power flow equations, represented by a column vector. So V bus 0 is equal to the column vector of V1, Vk, Vn. So these are the number of buses that you have in the system. And then we can solve the constant impedance using the ZIL to be Vi squared over the apparent power conjugated of the system or the line. And the changes in the network voltage caused by the fault with the impedance ZF is equivalent to those caused by the added voltage VK0. Okay? With all the sources short-circuited. So similar to the approach that we do in the Thevenin's theorem, where we zero the sources and then we remain with only the source where we have the fault. Okay, so in this case, zeroing all voltage sources and representing all components, what we have now is a Thevenin circuit. This is a Thevenin circuit where we've zeroed the sources, the other sources, and then we have our ZF. So our Thevenin's voltage then is equivalent to the Vk. So remember what we were saying previously, that if we have a Thevenin's network, okay, where we find the Thevenin's voltage in series with the Thevenin's impedance, then the network that is connected to this system, if we connect a system there, so if this is Vk 0, then the Thevenin's voltage, V Thevenin, because these two are in parallel, sorry, let me make that a circle, then the Thevenin's voltage, these two being in parallel, are going to be the same. So this is the scenario where you have our V Thevenin here being equal to Vk0. Okay? And then from there, from the theorem now, the Thevenin's theorem, we could say that the V bus 0, or the V bus at the faulted bus, which is there, will be equal to V bus 0 plus the change in the bus voltage. So we can express the current in the system, as you remember very well from load flow analysis, is that the current in the system is equal to, or on a bus, is equal to Y bus multiplied by V bus. Y bus being the admittance matrix, okay? And then this is the column vector, or the bus voltages at various buses. From this circuit then, we are able to determine, to say the current entering every bus is 0, because you remember we're zeroing all the sources, except at the faulted bus. So at the faulted bus, the current is taken as a negative because it is leaving that faulted bus. If you can see from the network, we have a bus, and then that faulted current is leaving this bus. And because it's leaving that bus, we'll take, if this is bus K, we take that current as IK with a minus. That means it's a negative injection. Okay? That is a negative injection bus current. And therefore, this is equal to the admittance multiplied by the change in the voltage values for all the buses. And this is what we have here. So I bus is equal to Y bus multiplied by the change in the bus voltage. But then when we come to solving the changes in the bus voltage, we get the change in the bus voltage to be equal to Z bus multiplied by I bus. Okay? Z bus multiplied by I bus. And we know that we can calculate or determine our Z bus, or Z bus is simply the inverse of the admittance matrix, or the Y bus. And this Z bus is what we call the bus impedance matrix. There are several ways you can determine these, mostly two. One is by building, and next is by using the inversing approach. Okay, so when we combine the equations, the bus voltage during the fault becomes then V bus F to be equal to V bus 0 plus the change in the bus voltage, which we have, that component now can be replaced by Z bus multiplied by I bus. This is the V bus. And so it means that our from this equation we can determine the bus voltages during the fault to be these variables, that is V1 to Vn, to be equal to the bus voltages, the initial bus voltages, that is V1 to Vn, plus the change in bus voltage, which can be solved from the bus impedance matrix multiplied by the fault current at the bus. Now, because all the variables are 0 except where the fault is, so we only have this element in the on bus K. That is the minus IKF. And because of that, because we have the non-zero elements being only this current vector in the kth equation, then it becomes our Vk, the voltage at the bus during the fault is going to be Vk0 minus Z double K IKF. So from the Thevenin circuit, then we are able to determine that our VKF is simply ZF multiplied by IKF. For the bolted fault, ZF is equal to 0 and VKF is going to be equal to 0. Okay? And for the fault current, IK is going to be equal to VK0 over the sum of the impedances, which is now the impedance, the fault impedance ZF plus the impedance at bus K. So for the fault at bus K, then we only need the Z double K element of the bus impedance matrix. And if we are to write the ith equation in terms of matrix equation, then our VI is going to be equal to VIF for any bus I, for instance. Then we are going to have VI initial value minus ZIK I current at that particular, the fault current at that particular bus. And if we substitute IKF, then, which is this component, into this equation, if we bring this component into this equation, then what we have is ZIK multiplied by VK over the sum of the impedances the self-impedance at bus K plus the impedance, the fault impedance ZF. So for a line connecting bus I and J with impedance Zij, the short circuit current therefore can be determined from this equation, where we get the Ij, the fault current will be equal to VIF minus VJF over the impedance Zij. So we're looking at two buses where you've got bus 1 and bus I and bus J, and then you're looking at the current flowing from bus I to J, which is defined as a positive current in this case. Therefore, you've got the voltage, similar to node voltage analysis, the way we calculate the current. So the current is flowing from a higher potential to a lower potential over the resistance, in this case over the impedance. So we get our current Ij during the fault to be equal to VIF minus VJF Zi. And like I said, there are two ways that we could use to calculate the Z bus. We could formulate the Y bus initially, and then find its inverse. So we are saying we know that we're able to determine the Y bus. Once we calculate the Y bus, then our Z bus is simply Y bus inverse. So when we calculate the inverse of the Y bus, then we've calculated the Z bus. This is one method. The other method is to build the Z bus. Okay? Is to build the Z bus. Build and assemble the Z bus by adding one network element at a time. So this, you can follow up how to build the Z bus matrix using Hadi-Sadat chapter 9.5. But in our case, most of the scenarios that we are going to look at are going to be maximum for the classroom purposes. We're going to look at buses from 2 to 3 only, maximum of 3, which is very easy to use the inversing of the matrix. But for larger systems, then it is advisable. Then it becomes very difficult to do the inverse by hand or manually. But you could still use the inverse using software such as MATLAB, where you could use the code to do the inversing for you, and then it's easier to run the code that way. But by hand, the more buses you have, buses more than 4, it becomes very difficult to do the inversing manually. So in our case, we rely and look at more examples in 2-bus and 3-bus systems. Okay, so let's look at an example. So this example is coming from the book Hadi-Sadat. His book, the example is 9.2, example 9.2. But the question says a 3-phase fault with a fault impedance ZF equal to J or yod 0.16 per unit occurs at bus 3 in the network of example 9.1. I'll show you example 9.1 so that you can have an idea of what we're talking about. Using the bus impedance matrix method, compute the fault current, the bus voltages, and the line currents during the fault. Now, this scenario is a balanced 3-phase system. Okay, so in this example, the bus impedance matrix is obtained by finding the inverse of the matrix, like we said. And then, if you check 9.5, like I said, you can see the other methods to build the bus impedance matrix. And for us to find the bus admittance matrix, we have to have the admittance admittance diagram. Now here is the circuit that has been given. The circuit has been given with impedances. So we are converting these to admittances, then we find the Y bus, and then we convert the Y bus to the Z bus. So this is example 1, where the question says the one-line diagram of a single three-phase bus system is shown in figure 9.1, which is this one. Each generator is represented by an EMF behind the transient reactance. All impedances are expressed in per unit on a common 100 MVA base. And for simplicity, resistances are neglected. The following assumptions are made. 1. Shunt capacitances are neglected, and the system is considered on no load. Number 2. All generators are running at their rated voltage and frequency and rated frequency with their EMFs in phase. You have to determine the fault current, the bus voltages, and the line currents during the fault when a three-phase fault, when a balanced three-phase fault with a fault impedance of ZF equal to 0.16 per unit occurs. Now this and then occurs on A, bus 3, B, bus 2, C, bus 1. In this example, we're going to look at bus 3, and I will encourage you to repeat the process to find when the fault impedance occurs on bus 2 and bus 1. Okay, so this is our admittances and the network. This is our Thevenin's voltage. This is our fault impedance, which is J0.16. And so we're looking at the scenario when the fault is applied on bus 3, on this bus. For you, please repeat the process on bus 2 as well as on bus 1. Now, by inspection, then we're able to determine the Y bus. I'm sure you remember how to determine the Y bus. So by this, we determine our Y bus to be as follows. So this is a 3-bus system. We determine our Y bus is going to be a 3x3 matrix. 3x3 matrix. So this is our Y11, Y12, Y13, and so forth. This is Y21, Y22, Y23, Y31, Y32, Y33. Okay? Then we take the inverse of this matrix. You can use the LU decomposition method. You can use the determinant approach to come up with the inverse of this matrix. And so this Z bus is determined from getting the Y bus inverse. And this gives us these variables. In some cases, we like to write this, we externalize the J, and then we put our variables in the matrix like so. So in some other textbooks, this is what you are going to see. Okay, now that we have our Z bus calculated, let's find the fault currents. Okay, so the fault current at bus 3 with the fault impedance ZF per unit is therefore going to be equal to Z33. So Z33, this is coming from our Z bus, which is, if I go back, so what we have now is that from here, you remember I was saying this is y 1 1, this is y 1 2, this is y 1 3. Equally, here we've got z 1 1, z 1 2, z 1 3. This is z 2 1, z 2 2, z 2 3. So this is our z 3 3. Now, because the fault occurs on bus 3, our consideration, our key variable here is our z 3 3 that you will see being applied. Okay, so our current, therefore, the fault current at bus 3 is equal to V30 over Z33 plus ZF, where we said our V3 is assumed as 1 per unit over J 0.34 plus J 0.16, giving us J minus J 2.0 per unit. The bus voltages and short circuit currents during the fault then can be calculated as follows, where you have our V1F during the fault to be equal to V10 minus Z13, also coming from the Z bus. I3F, which we have just calculated, so our I3F is this variable that we just calculated, and then our V10 is 1 per unit, and then our Z13 is 0.12, and we get 0.76 per unit. Equally, we can determine V2 and V3 during the fault to be equal to these variables, V2 being 0.68 per unit and V3 being 0.32 per unit. The short circuit currents in the lines are therefore between, so we've got 3 buses, bus 1, 2, and 3. So we're looking at the lines now connecting these. So this is bus 1, bus 2, bus 3. So I12 is the current flowing from bus 1 to bus 2 during the fault, will be V1F minus V2F over Z12. So we're looking at the impedance there, Z12. And you have the voltage during the fault, V1F, on bus 1, and on bus 2, you've got V2F. And these we've determined from here. We already determined the bus voltages. So it's just plug and play. You put in the values there, and we get I12F to be minus J 0.1, I13F to be minus J 1.1, I23F to be minus J 0.9 per unit. That is for a balanced 3-phase system. So in here, it is pretty straightforward. You can repeat the process for the fault on bus 2 and bus 1, and you get your solutions. Now, when we come to unbalanced faults, balanced faults, I did already introduce them in the symmetrical components and unsymmetrical faults, which is the previous video. If you can watch that previous video, then you will see that in order to obtain the unbalanced faults, the bus impedance matrix have to be for each sequence. Now, when we looked at symmetrical components or symmetrical unsymmetrical faults or symmetrical components, you've got the 3 sequences, okay? You've got the positive sequence, you've got the negative sequence, and you've got the 0 sequence, okay? So you've got your current variables here. This is the zero sequence where your currents are equal. Okay, you've got your your positive sequence, where if this is your A, you've got your C, your B, and then you've got your A, B, C. That's your negative sequence. Okay, and we said, and this is the zero sequence. So you can revise through the notes and see. So for us now, we have to find, for this scenario, we have to find the Z for the positive sequence. The positive sequence is 1, it's taken as 1. The negative sequence is taken as 2. The zero sequence is taken as 0. Okay, so we have to find these sequence impedances. And then the connection of the sequence impedances, if you remember, depends on the connection, on the type of fault. So if you've got a line to ground fault, then you can see how these networks are connected, like we looked at in the previous scenario. So if I can show you quickly how these scenarios are going to be, before I come to the equations, I just want to quickly take you through the behavior of the system. So this is what we looked at last time, and we said that if we have a line to ground fault, what is going to happen is that we are going to have the sequence elements, positive, negative, as zero sequence networks, all connected in series. Okay, all connected in series. And if we add the ZF, which is the fault impedance, then this is the fault current that we are able to determine. So they are all connected, and then you can see all the elements, the zero sequence, the positive sequence, the negative sequence. This is zero, positive, negative sequence, all connected in series, and you've got 3 VF added there coming from the fault impedance. So this is the connection that we mean, that first we have to determine the bus impedances for each sequence, which is the zero sequence, the positive sequence, the negative sequence, and then connect them depending on the network setup. So if it's line to ground, this is how they are going to be connected, or in series. If it is line to line, what you're going to have is that you've got the positive sequence connected in parallel with the negative sequence, whereas the zero sequence is decoupled, is disconnected. So I0 is 0. So this is the way the network is going to be connected when you're dealing with a line-to-line fault. When you're dealing with, in addition of the fault impedance, then you simply add that fault impedance to the impedance for the zero sequence, for the positive sequence and the negative sequence. And if you come to the line to ground fault, so you have the positive sequence fault current connected in parallel with the negative sequence, and so you've got and also in parallel to so these two are parallel, and when you add these two, then this becomes in series. So you've got the positive sequence impedance connected to the combination of the negative sequence and the zero sequence in parallel. So these are added in parallel and then added in series to this. So this is the network connection that I'm talking about. And for the unbalanced using the Z impedance, then we have to find the Z for the zero, the impedance for the zero sequence, for the negative sequence, and for the positive sequence. Okay. So coming back to what I was explaining here, when we have the unbalanced faults, so we have to determine the sequence impedances, that is Z0, that's for the zero sequence, this is for the positive sequence, and this is for the negative sequence. And the connection I just showed you depends on the type of fault that you have, whether it's a line-to-line, line-to-ground, line-to-line-to-ground fault. Okay, now let's look at the single line-to-ground fault using the Z-bus. What you have here is that we are considering all these faults connected, or the fault going through the fault impedance ZF. And in here, this to solve requires that we have the zero sequence, negative sequence, positive sequence networks for phase A to be placed in series, that is in the connection in series, and then that's how we can find the zero sequence fault current. So the zero sequence, then the fault current on bus K is going to be, for the symmetrical components, they are going to be equal. Remember, they are connected in series. So you've got the zero sequence connected in series to the positive sequence, connected in series to the negative sequence, and therefore the current flowing in that loop is 1, which is simply IK0 equal to IK1. So this is zero sequence, positive sequence, negative sequence, which is going to be equal to VK0 Z1KK plus Z2KK plus Z0KK plus 3ZF. These are impedances that you are going to find per symmetrical component element or sequence, per symmetrical sequence. And then here you have, so these are, like I said, are going to be your diagonal elements in the k-axis of the corresponding bus impedance matrix. So Vk is the pre-fault voltage at bus K, and the phase fault current, therefore, for phase A, B, and C can be found from IK ABC to be equal to A. This A is, so we know from our sequence components that our A is equal to 1, 1, 1, 1, 1. You've got A squared, A, A. So this is a matrix where we know our A equal to 1 at angle 120 degrees. That's our A. So our A squared is simply 1 at angle 240 degrees, or is equal to 1 at angle minus 120 degrees when you take the other route on the phasor diagram. Okay, so this is what we have. This is our A here. So I can write it properly. That's our A. And this is the zero sequence, positive sequence, negative sequence. And then if we consider line-to-line fault using the Z-bus, equally we have the same. Just as we mentioned, we are going to be, our circuit is going to have the positive sequence parallel to the negative sequence, or in opposition. So the current is going to be simply the negative. So the current flowing in the positive sequence is equal to the negative current in the negative sequence. Whereas the zero sequence component is decoupled, so it's separated, and for this reason IK0 component is 0, and then we can determine now our IK1, which is the fault current, to be equal to VK0 over ZK1, that is the positive sequence, that's the negative sequence, plus the fault impedance. So these, as we mentioned, these are diagonal elements in the K axis of the corresponding bus impedance matrix. The phase fault current is determined similar to the previous case that we looked at. For the double line to ground fault, this is where you've got a line to line and then two grounds through a Z fault impedance. Then the positive sequence impedance is placed in series with the parallel combination of the negative and the zero sequence. I'm sure you remember this. What you have is that you've got the parallel combination of you've got your zero sequence, your positive sequence, so we can say like so, and then you've got your negative sequence is in parallel with your zero sequence element. Okay, so these two are solved as parallel and then connected to the positive sequence, and therefore what you get for the currents is that you get now VK0 over Z1 double K, which is answering for that, and then these two are they're in parallel. Obviously we can add the fault, which is 3ZF, which is in series with the zero component, okay, which is in series with that. Okay, so we get Z2KK, or sorry, the 2 can be here. This multiplies by the sum of these two, which is Z0 double K plus 3ZF, and they sum up. So Z2KK, because it's a parallel, we're dealing with a parallel impedance here. So this is plus Z0KK plus 3ZF. And this is what you see here. This is what you see here. Okay? This is a parallel system that is added now in series to this system, and we obtain our equations like so. Okay. And then our IK2 is simply minus VK0 minus Z1 IK over the Z2KK, and then IK0, you've got the series there, the current in that loop that I just deleted here. So you've got the 3ZF in series with ZK, Z0, and this is the current passing through there, is Vk minus that over that. So this is how we solve the fault currents in such systems. And then for us to find the phase currents, we get IK ABC to be equal to A. I mentioned already what A is. This is just a transformation matrix. In this case, our transformation matrix being equal to that. Okay, this is our transformation matrix A multiplied by, so this is the sequence components or the phases A, B, C, and then these are your sequence components, 0, positive, negative sequence. Okay, and we are able to determine our fault current to be equal to IKB plus IKC. Then the voltages are also solved following the same symmetrical components of the ith bus voltages during the fault. These are obtained from, this is for the zero sequence voltage during the fourth fault. This is equal to 0 minus ZIK, zero sequence, IK, zero sequence. VI during the positive sequence during the fault, this is equal to VI1. This one is representing the positive sequence. The initial value minus ZIK1, IK1. And then for the negative sequence, you've got VIF being equal to 0 minus ZIK 0 negative sequence and IK negative sequence. And these are the pre-fault voltages at bus I. So VI10 equal to VI0. Okay. And you can determine the phase voltages during the fault to be VI phase A, B, and C to be equal to A, VI, 0 sequence, positive and negative sequence. So this is how we solve using the Z bus. Okay. And we can equally determine the symmetrical component currents or fault currents from line I to line J given by these following equations. As we said, we are looking at bus I going to bus J. So this is your bus I and your bus J in that sense. And so for the zero sequence currents, positive sequence currents, and negative sequence currents, that is what you obtain. Okay, so your impedances are going to be varying. Like we said, you've got your zero, you have to calculate your Z bus for the zero sequence, Z bus for your positive sequence, Z bus for your negative sequence. And this is why you have the impedances here being the impedance IJ, ZIJ for the zero sequence. This is for the positive sequence, and this is for the negative sequence components of the actual line impedances between buses I and J. And the fault currents from I and J, in terms of the phase fault currents, you can find them as IJ, ABC to be equal to A, IJ, where A is, as I already told you, A squared, A. And that is how we solve. Now, let's look at, so for the unbalanced system, you've got a number of activities to look at. One is, let's assume the generators are are given as follows. So the generator variables, impedances, which is for the positive sequence is equal to the negative sequence is equal to J0.2, and for the zero sequence we have J0.05. For the transformers, we assume the positive sequence impedance is equal to the negative sequence impedance is equal to zero sequence impedance, which is J0.005. For the lines, assume the Z positive sequence impedance is equal to the negative sequence impedance is equal to J0.1, and the zero sequence impedance is J0.3. Assume the unloaded pre-fault with voltages equal to 1.0. So the pre-fault voltages is 1.0. Now, so if we are to solve for the impedances, so this is our network now in the positive sequence. The variables we've been given, we have, if we go back, these are the variables we've been given for the positive sequence. This is what we have. The positive sequence is equal to the negative sequence for the generators is J0.2. So this is going to be J0.2. For the transformers, we have J0.05. And then for the lines, positive sequence equal to negative sequence, we have J0.1. So what we see here is for the lines, we've got J0.1 in the positive sequence for all the lines. This is for the transformer reactance, and then this is for the generator. So this is the combination of the transformer and the generator. Remember, the generator was J0. I think 2, and then for the transformer we had J0.05. So when we add the two, because they're in series, we get J0.25. So this is what we get here, and this is what we get equally there. Okay? By inspection, you come up with the Y-bus. So you determine the Y-bus for these 3 buses. So the Y-bus is developed this way. Then you use the inversing to get your Z-bus. So your Z-bus is the inverse, is the Y-bus, the inverse of the Y-bus, and this is what we obtain. So this is the Z-bus for the positive sequence. Take note of that. But we are also informed that the Z-bus for the positive sequence, or 1, you can take it as positive sequence, is equal to the Z-bus for the negative sequence, 2, which you can also write as plus equal to Z-bus minus. Okay? So this is how you solve the Z-bus for the positive sequence, and then you solve the Z-bus. This is for the zero sequence, because for the positive sequence, we know it is equal to the negative sequence. So for the zero sequence, again, we know this is disconnected. So the zero sequence element is disconnected, and then we have the negative sequence. So these are the variables for the zero sequence. The impedance in the lines was 0.3 for the negative sequence. And then here for the generator, it was 0.05. For the transformer, you have 0.05. And then you have here for the transformer, you have 0.05. This is disconnected from the system because of the zero sequence. And therefore, we determine the Y-bus based on this network. We get our Y-bus for the zero sequence, and again we get our Z-bus for the zero sequence to be the inverse of the Y-bus for the zero sequence. Okay, and this is what we get. So after that, now we are able to get for the single line to ground fault at bus 3. So what we have, this is the Thevenin voltage and the Z bus diagonals. This is for the positive sequence. This is the Thevenin circuit that we obtain. This is the negative sequence, and this is the zero sequence. Then the fault type, like I mentioned, the fault type now determines how the networks are interconnected. Okay, if it's the line to ground fault, then you connect these networks in series. If it's the line to line fault, okay, you connect the positive and the negative sequence. The zero sequence is decoupled. If it's for the double line to ground fault, you connect these in parallel and in series to this network, and then you add the fault impedance in the circuit. So at bus 3, the single line to ground fault, as we said. So in this case, you have the V0, the initial voltage at bus 3, which is 1.0 at 0 degrees. And then you have now, because the elements are connected in series, so our current is going to be determined like so. Okay? Our current is going to be determined like so. And equally, if we have the ZF in the network, so it's going to be added to this fault current for us to determine with the fault impedance. So the current, fault current during the positive sequence is equal to the current during the in the negative sequence equal to the current in the positive sequence, because they're in series, and this is what you obtain. The voltages are obtained from, remember we had V positive sequence is going to be equal to your V plus Z I bus. Okay, Z I. So if you're dealing with the positive sequence, that is your V0 during the positive sequence. This is a Z bus during the positive sequence multiplied by the I bus during the which is the fault current period. Okay, I bus F. Okay, and this is what we obtain. So our positive sequence voltage gives us these voltages, and then our negative sequence, we obtain our value to be Z bus multiplied by the current, and this is what we obtain. Our zero voltage component is going to be given as follows. Okay, then we can calculate the phase voltages at any bus, meaning our V3, our V1, our V2, that is bus 3, bus 1, can all be calculated from this, where we now get our A multiplied by the sequence voltages that we found. In most cases, the unbalanced faults using the Z bus, we're looking at the faults on the lines. Now, if there's a fault on a line, usually what we do is we create an artificial bus or a dummy bus, what we call a dummy bus on a line, and then we split the impedance of that transmission line, depending on the fault location, if it is halfway, if it is 3/4, depending on that. Then we now have to, so this is a dummy bus, which we can add up in a line if the fault is on the line. So if we have a fault on the line here, and you may be told the distance allocation of this fault, it is half the transmission line or any other distance, then this is how you determine your fault. You create a dummy bus, and using that dummy bus, so it becomes from a 3-bus network, you have a 4th bus network, and then you go ahead to derive the Y bus based on the additional 4th bus that you are given. And then from there you can determine your Z bus for the positive sequence, negative sequence, and so forth. There is a good example that you can look at. This example is in Hadi-Sadat, example 10.6. In Hadi-Sadat, follow it step by step. It has got very clear explanations on how to solve when the system is unbalanced. Thank you for your attention. See you next time.